Hello folks, and welcome to this lesson on Born-Haber cycles. By the end of this lesson, you should be able to draw Born-Haber cycles for various ionic compounds and solve problems related to Born-Haber cycles. Now before we actually go into what a Born-Haber cycle is, I want to recap the ionic equations that we talked about back in grade 11. So if you recall, the ionic equations are those equations that show how an ionic compound is formed. So basically, one of them has to do with the loss of electrons to form the cation. One is to show the gain of electrons to form the anion. And then the third equation itself is taking the anion and the cation and putting them together to form that ionic compound. Now the thing is that this is relevant to your enthalpy related topics, your energetics, because there is energy associated with every single one of these steps. When we're looking at the loss of electrons to form the cation, well, that's basically ionization energy. And when it comes to the gain of electrons to form the anion, the energy that is associated with that is electron affinity. Now there is another one, and that's the electrostatic attraction between the anion and the cation. That is one that is a little bit newer, but I should have talked about that in the definitions lesson. And this, the energy associated with this process is lattice enthalpy. So Born-Haber cycles, reactions are going to be happening. In the past slide, I talked about the formation of ionic compounds. So you're probably going to have to use all of these values in some way or another. Now I do want you to be a little bit careful and keep in mind that states and all of that are very important. So for all of these, we're looking at isolated atoms. So we're not looking at your Cl2s, your O2s, or anything like that. We need it to be just Cl on its own, and everything has to be in gaseous state as well. That's how those definitions for ionization energy and electron affinity work. It's 1 mole of the thing, it's an isolated atom, and it's in gaseous state. I also want to remind you of the existence of lattice enthalpy once again and its definition, and also enthalpy of atomization. If you don't remember what they are, go back to your notes and take a look and keep them in mind. Alright, I have a challenge for you. So after I show you the information, pause the video and try it out. But what you're going to do is, using only your data booklet and the following information, find the enthalpy of formation for sodium chloride and represent this information as a graph. So in other words, those enthalpy level diagrams, you're basically going to show an enthalpy level diagram for the enthalpy of formation for sodium chloride. So information from your data booklet, and also 2 other pieces. The delta H of atomization for chlorine is 121 kilojoules per mole, and the delta H of atomization for sodium is 107 kilojoules per mole. So pause the video, draw me an enthalpy level diagram that shows how to get the enthalpy of formation of sodium chloride using what's in your data booklet. Alright, did you get negative 415 kilojoules per mole? And did you come up with something that looks like this? If you're sitting there bewildered at the task that I have given you and what I'm showing you right now, don't worry, we're going to go through it together. Also, I want to note that technically the delta H naught of formation for sodium chloride is actually negative 411 kilojoules per mole, but the numbers that you're going to be dealing with are going to end up at negative 415. Alright, first off, I just want to say that this is a Born-Haber cycle. And a Born-Haber cycle is an energy cycle for the formation of certain ionic compounds. So if you remember the Hess's law questions where you had to be able to use a cycle diagram to be able to show how certain reactions work, this is basically that, except a lot more. It is basically an application of Hess's law. You are basically taking all of these different reactions, putting them all together to get this final value. So at the end of the day, it's just a really, really long and big Hess's law question. Now, why do they exist? Well, you can get some information from them that would be harder to obtain in other ways. So it's not going to be necessarily easy to find out lattice enthalpy because everything, all of your ions being in gas and then having them form a solid ionic compound, that's not something that you can easily do experimentally. But on the other hand, there are devices that you can use to get things like ionization energy or electron affinity. So you can use these other values to get some values that are harder to get in any other way. So how do you create a Born-Haber cycle? How do you draw one of them? Well, the first thing that you have to know is that basically what you're doing is you're starting with the elements in standard state, and the end of your Born-Haber cycle is the ionic compound in solid state. So once you have your elements in standard state, atomize them. So basically anything that isn't already in gaseous form, you're going to turn into gaseous form. And if you have anything diatomic, well, that's going to need to be broken up into the individual atoms as well. Then you make sure your cations are going to become cations and your anions become anions. The energies associated with these are your ionization energies and your electron affinities. Something to keep in mind as you're doing all of this is the fact that you might need second ionization energies or third ones. Same thing with electron affinities. If you have ions, or if you're going to end up with an ionic compound that have ions that aren't a +1 or -1 charge only. Anything more than +1 or -1, you're going to need second and or third ionization energies and electron affinities. And then the last piece that you're going to need is lattice enthalpy. And once you put all of those together, you're going to end up with that, with the delta H naught formation of your ionic compound. Or in some cases, depending on the problem, they will give you, or you will have the delta H naught formation of your ionic compound, and you need to find one of those other values. So if that's the case, let's construct a Born-Haber cycle for sodium chloride together. So let's start with our energy. We're going to start with our beginning and we're going to start with our ending. I am cheating here. I know that this is going to be exothermic, and so I have your products further down, but this is not always going to be the case in terms of enthalpy of formation for ionic compounds. Do note that I made sure that I am following that definition. I have 1 mole of that ionic compound and I've made sure that everything is balanced. These are starting in standard state. Alright, first thing that we're going to do is we're going to start atomizing. Now with the Born-Haber cycle, when you're drawing this, you're going to go literally one step by one step. So we're not going to atomize both of these things all at once, we're going to atomize just the one. So I'm going to choose to atomize sodium first. So we're going to go from here and we're basically going to go and make sodium into gas. And we have done nothing to our chlorine yet, and this is going to be our first stop. Now the change to go from here to here is that delta H naught of atomization for sodium. We have 1 mole's worth of it, and so that number is going to stay the same. From here, theoretically, you can just start atomizing the chlorine and then go from there, but with a lot of the Born-Haber cycles that you see, you're going to find out that they take one of the elements that are involved, do all of the steps to make it into its ion, and then do all of the steps to make the other one into the ion after that. So let's take our sodium and let's make it into an ion. So we've taken our sodium, we've taken out an electron, and we have the energy associated with this. Now something that you're going to notice with what I've drawn is that I have not made these properly proportional. Ideally, if you have the space to be able to do that, it would be nice, but I am going for saving space. I'm not going to have space to do everything else that I need to do if I made everything perfectly proportional. Now, in this particular case, our sodium only needs to have a +1 charge, so we only have 1 ionization energy. But for example, if you were going to use something like magnesium, and you take your magnesium, you have already atomized it, then the first one, you're going to go one step and make the +1 ion, and then you're going to take another step to make it into the 2+ ion. And then the energies associated going from here to here and there to there is going to be your first ionization energy and your second ionization energy. But again, you're going to do it step by step, every single process by process. All right, at this point, we've gotten to the sodium ions. Sodium has gone as far as it needs to go, so let's deal with our chlorine. So first thing that we have to do is atomize your chlorine. And that process is another endothermic process, and so we are now up here. Now I've extended this line because I know what's coming next. And what's coming next is we are going to ionize our chlorine. Now, when we are ionizing chlorine, the energy, it's becoming an anion, it's gaining an electron, and the energy associated with that is electron affinity. And I already know that the electron affinity of chlorine is negative. It's an exothermic reaction. So when we're going from here to here, it is exothermic, and there's that value for it. And same thing here as it was with your cation. If you have another electron affinity, then you're going to add on to this. Now, something for you to note is that every single second and subsequent ionization energy is always going to be endothermic. And so what's going to happen in that case is that you're going to have to extend this further. And so after this first electron affinity, you're going to have to go up however much to put in that second electron affinity. So some of these Born-Haber cycles can look quite complicated. Now the last piece here in terms of the steps that we're looking at is that lattice enthalpy. Now by definition, lattice enthalpy is going to be going that way. You're going from the solid ionic compound, 1 mole of it, and you're breaking it up into its ions in gaseous form. And so the lattice enthalpy goes in here. And so the final part of this is answering the actual question, what is the delta H naught formation for sodium chloride? Well, you basically take all of these numbers, everything that goes up is going to be added together, anything that goes down is going to be, you're going to subtract it, and with that lattice enthalpy, because we're trying to find out what this is overall is going down, we're going to have to flip this, and so you would be subtracting that. And as a result, you get the value of 415. With these particular values. So as you might be able to tell, the hardest part about Born-Haber cycle related questions is going to be remembering everything. Every single step, every type of enthalpy that you're going to need to use, remembering that sometimes you're going to need to do first and second IEs or EAs and all of that is going to be the complicated part. So the types of questions that you can get for Born-Haber cycles is, if people are being very unpleasant, they'll make you draw one. There is also the option of, here are all of your values, figure out one of these other ones. So I might give you literally everything else and then make you figure out what the delta H naught of atomization for sodium is. Those are going to be the general types of questions that you get, but you are going to need to familiarize yourself with being able to read a Born-Haber cycle and being able to draw one as well. That's the end of this lesson. I'll see you next time.